Okay, so these are the outputs activations that we can use for different problems. Now I want to talk about the different variants of the ReLU. So in the 2010s, the ReLU became very popular. In 2011, it was found to work better on deep neural networks. And as of 2017, it is apparently the most popular activation function. So all of these variants that I will now show you have outperformed the regular ReLU, at least on some problems and according to some papers. So the first variant is called Leaky ReLU, or LReLU, and this solves the dying ReLU problem. What it does is instead of setting the activation to be 0 if x is negative, it sets it to be a very small number times x. So it looks like this, basically. In blue, you have the regular ReLU, and in orange, you have the Leaky ReLU. And because now we do have values here, so even if all the inputs to a neuron are negative, it can still move and still function. It can still move. So the gradient is not 0 and weights can still move with the Leaky ReLU activation function. And so we don't suffer from the dying ReLU problem. And this activation was introduced in this paper, which is written over here. Another variation is called Parametric ReLU. It's just like the Leaky ReLU, only the alphas are now parameters of the models, and we learn them, we optimize for them during the learning process. And this was introduced in this paper over here. Another variant is called the Exponential Linear Unit, or the ELU. And it looks like this, okay? And this is the function that creates it. In blue, you have the regular ReLU again, and in orange, you have the ELU function. The main thing that this does is that it helps with the bias shift problem. So because here we have larger negative value, the mean of the outputs of the activation will be closer to 0. So the problem with Leaky ReLU is that, yeah, okay, it solves the dying ReLU problem, but the mean of the activation will still be much greater than 0 because most of the values are much greater than 0. And this still creates the bias shift problem. But here we have much greater negative values. So here the mean will be closer to 0 and we won't suffer so much from the bias shift problem. This was introduced in this paper over here. Another variation is called the Scaled Exponential Linear Unit. So it's very similar to ELU, only it has some more parameters that have a specific value. So yeah, this is basically the alpha from the ELU, and then you multiply both terms by this value over here. You can see the difference between the ReLU and the SELU, which looks like this. Now, what's the motivation behind this? Well, it turns out that the outputs of the SELU activation tend to have mean 0 and variance 1 or standard deviation 1. And so this can be thought of as an alternative to batch normalization because it drives the mean of the activations to 0 and the variance to 1. This is exactly what batch norm does. And we will discuss batch norm in a future video. But why do we even need an alternative to batch norm? Why not just use batch norm? Well, the problem is mostly with feed-forward neural networks. So with convolutional neural networks and recurrent neural networks, you can do very deep networks and get really successful results. But feed-forward neural networks, they seem to suffer when going to deep neural networks, and they are not as successful when using deep neural networks as their CNN and RNN counterparts. So why is that? Well, the authors of the paper, of this paper over here, they argue that CNNs and RNNs have weight sharing property, and this makes them more robust to the stochastic perturbation of normalization techniques like batch normalization. So basically, batch norm kind of allows you to go deeper with networks. CNN and RNN are a bit more robust to the stochastic nature of the batch norm, which only uses information from batches and not the entire data set. But feed-forward neural networks don't have this weight sharing ability, so they are less robust to the batch norm stochasticity. And so using SELU kind of alleviates the problem. You can use them on feed-forward neural networks. The outputs are still more or less with mean 0 and variance 1. And you can go deeper with feed-forward neural network using these SELUs. And the title of the paper is Self-Normalizing Neural Networks because these activations kind of self-normalize. Instead of using batch normalization, you use these activations and you get that the outputs are normalized. Okay, another variation is continuously differentiable exponential linear unit, or SELU with a C. The problem with ELU is that it's not continuously differentiable unless alpha is equal to 1. So there's a slight modification to the ELU function. Instead of having x here, it's x divided by alpha. And what it does, it makes sure that the derivative at this point is continuous. So here we have the derivative of the ELU function. We see that except for alpha equal 1, there's a jump in the derivative. And here we have the same derivative of the SELU function. And here we see that no matter what the alpha is, the derivative is always continuous at this point. And this is from this very short paper by this guy over here. Okay, another type is called GELU or GELU, Gaussian Error Linear Units. Okay, what happens here? We just multiply x by some CDF function, in this case, the CDF of a standard normal distribution. And this is how it looks like. Notice that here we have some non-monotonic bump. So it was first introduced in this paper over here. They made some changes to the paper, and the final version has this name, and it's from 2020. Okay, and this apparently works better for some problems. I won't go into the motivation of why this worked. They started with something different, then they somehow stumbled upon it, and it seemed to work well. In the same paper, they also mentioned that it doesn't have to be the CDF of a normal distribution. It can also be the CDF of a logistic distribution, which is just the sigmoid. So we can also have the SELU, the Sigmoid Linear Unit. It looks something like this, quite similar to the GELU. Okay, and now we have another function called the Swish. And this is interesting because this function was found using something called meta-learning. So in meta-learning, we are trying to use machine learning or neural networks to discover the parameters of the neural networks, or to discover the architecture of the neural networks, or in this case, to discover the best activation function of a neural network. So what they did is they used an RNN neural network, which output a string, and this string was the list of operations that we want the activation function to have. So maybe take the x and make it an exponent of x, and then take 1 over this exponent and maybe add something. So it had all kinds of different operations that it could use: addition, multiplication, division, exponentiating, logarithm, cosine, sine, etc. It gave out a certain activation function. Then they took this activation function, tested it on a classification problem. If I'm not mistaken, it was the CFAR10, and they got some validation error or validation accuracy. And this was the metric used to drive the RNN network or the RNN agent or the RNN controller to go and look for better activation functions using reinforcement learning. And so this was very neat, I have to say. So from this meta-learning space search, they found that this function, this activation function, was the best function. And it's interesting because this is an interpolation, depending on the beta over here, between if beta is equal to 0, this whole thing is equal to 1, and so it's just x divided by 2, so it's just a linear function. When beta is equal to 1, this is exactly the SELU from before, from here. And when beta goes to infinity, or even just greater than 5 or 10, it already really appears like a ReLU. So it's kind of an interpolation between a linear function, a SELU, and a ReLU. Now, beta itself can be a trainable parameter. You don't have to set it in advance. So quite a neat paper. It's called Searching for Activation Function. If you're interested, go and read it. And now a small quiz question. So why here we have a beta parameter, and we can also make it trainable, but it's not the point, where in the regular Sigmoid activation function, we don't need to use this beta. So notice this is the regular Sigmoid, only the regular Sigmoid doesn't have a beta here. And here all we do is multiply it by x. So now why is here beta plays a role? If you think you know the answer, please write it down in the comment to this video. Okay, another activation function is called Mish. It's defined like this. The Softplus is just this function over here. It kind of looks like the Swish or the SELU. It's from this paper over here. It apparently works better on some problems. I don't have anything else to say about it. Another interesting activation function is called the Randomized Leaky ReLU, or RReLU. And this is very similar to the Leaky ReLU, only at train time, you don't set a fixed alpha. You sample it from some uniform distribution between some lower and upper bound. And this seems to have some regularization effect. Okay, and this is how it looks like. Here, notice you don't get a specific value, you get some random value between a range of possible values. Here you can see the evolution from ReLU to Leaky ReLU to Randomized Leaky ReLU. So here you have the ReLU, here you have the Leaky ReLU, and here you have some randomized Leaky ReLU. If your input, let's say, is this value, you don't just get this value, you can get any value between here and here. At test time, you don't use the randomization, you just set it to be this line over here. Yeah, and again, this seems to have some regularization effect. There's not so much theoretical understanding of why this helps. It wasn't introduced in a paper, it was actually introduced in a Kaggle competition, which is this Kaggle competition over here. One of the winners of the competition used this, and yeah, he was one of the winners. So this seems to generate interest, and it's now also a known activation function. Okay, the final version of the ReLU that we will look at is called Softplus, also known as smooth ReLU. This is how it is defined to be. It's also equal to the integral of a sigmoid function from -infinity to some value x. There's a more complicated version of it where you also add some parameter like a beta, and you multiply it by 1 over beta. This is how it looks like. So in blue, you have the ReLU. In orange, you have the Softplus. You can see that it's basically this smooth version of a ReLU. So it converges with the ReLU for very big numbers and very small numbers, but in between, it does something like a smooth interpolation. And this was introduced in this paper over here. Okay, here is an image of some ReLU variants along with the derivatives. So in blue, you have the functions. In orange, you have their derivatives. Two main takeaways that you can have from this. One is that all the variants kind of look like a ReLU, more or less. Yeah, they look very similar to ReLU. And the second takeaway is that most of the derivative are bounded. And this is a good thing because otherwise we might suffer from the opposite problem of the vanishing gradient problem, which is the exploding gradient problem, which mostly occurs in recurrent neural networks. Okay, so these are the two main takeaways from this graph. I just want to mention two more activation functions. One is the Log-Sigmoid. It's defined to be this. It's basically equivalent to the Softplus. It's equal to minus Softplus minus x. Yeah, so instead of using it, you could probably use a Softplus function. The second is called the soft sign. It's equal to this thing over here. It looks like this. So it's kind of similar to a tanh or a sigmoid. The thing is that it's less saturated than the sigmoid or tanh, meaning the derivative for very high or very low inputs is bigger than the derivatives of a sigmoid or a tanh. Yeah, so you can use the soft sign activation to kind of overcome the saturation problem of sigmoids and tanh activation functions. Okay, there are many, many more activation functions. There are always new activation functions that people come up with. These were the main activation functions that I know, and I hope it gave you some intuition about the activation functions, why we use them, and how we use them. Okay, this is all for this video. Thank you, and see you in the next one.